Manin kernel is actually the torsion of the L point of the L of L. Okay?
I was going to ask you something related to that comment, and that is, do you have the same result in your generalization of the context of the question or the comment? In other words, if you're not assuming transcendence degree 1, in your context, do you have that same result, that the torsion points are...
Actually, that's
actually a sharp. A sharp is a torsion group.
That is actually a Colchin closed set.
Right.
I don't know.
You don't know?
I don't know. Yeah. I actually don't know. That would be interesting.
Yeah.
If it actually is, that would be interesting. In some cases, I'm sure there are some cases in which it is. Trying to think of, for example, yeah, no, I'm not sure. I'm not sure.
Yeah.
Okay. So we have this. Then Khrushchevsky-Sokolovich, and this is a deep theorem. This is a very deep theorem, and this is at the heart.
I'm just going to ask you how you prove that.
Oh no, this is okay. But yeah, this uses a lot of machinery actually from model theory of finite Molly wranglers.
Wow.
This is really the core of the dichotomy, the way Khrushchevsky proved dichotomy for differential fields, which he used to prove the model lamp for function fields. So okay, so this is a really deep theorem, but okay, we get this. So we get an A, finite Transcendence degree, constants are C, but it's not constrained. Why is it not constrained?
Wait, I have to absorb that.
Right, so we're trying to build this counterexample.
You're taking a generic point.
A generic point.
Of this variety, of
That's
A sharp.
That's right, of A sharp. Finite Transcendence degree over K.
And it's not constrained?
And it's not constrained. This A is not constrained over K.
Oh.
It's not constrained over K.
Would it be in that differential closure if it were?
Okay, no, the reason, I don't think that the reason is because this is a Colchin closure of Tor A.
Oh.
Okay, so what this says is that if I take the n torsion holes.
Yeah.
This is a finite. So in particular, it's a proper subgroup.
Right.
Of this.
Yes.
It's a proper subgroup. The n torsion is a proper subgroup. Right?
Yes.
But as I vary n, the union as I vary n, right? This is Colchin dense.
That's right.
This is Colchin dense.
Yes.
Colchin dense.
An A. Oh, an A sharp.
Right?
Colchin dense in A sharp.
Colchin dense in A sharp.
Yeah.
Right?
Yep.
So I have these proper subvarieties where if I take the union, they're dense. And constraint was exactly that the union of the proper subvarieties was containing some proper subvarieties.
There's a message from Ronnie.
Okay.
Can read it? I'll pull it up.
Okay.
So he said that using strong minimality, I think you don't have to assume that transcendence degree is 1.
You don't have to.
Yeah.
Okay, so maybe
That's a comment to the previous comment.
So if you under a strong minimality, then this A sharp is equal to the torsion of A. But this thing. This thing is strongly.
What does it use?
It's strongly minimal. The thing is strongly minimal, so it's easy.
Just a moment, you'll see it on the screen.
I don't trust this technology, so I'm not sure.
You're saying that A sharp is strongly minimal? What's strongly minimal?
So A sharp, A sharp is strong. As long as you start with a simple abelian variety, A sharp is a simple.
And
A sharp is strongly minimal.
It wouldn't matter if it descends to constants or not.
Yeah, A sharp is strongly minimal.
Makes sense.
Yeah, the thing is that, I mean, you show that if you take a strongly minimal set in A sharp, then you use some definability things to show that if you remove finitely many points of A sharp, you get that strongly minimal subset. So the difference between A sharp and a strongly minimal will be only a finite subset. So you will get the A sharp strongly minimal. But, so I think I need to think about that. Yeah, A sharp is strongly minimal. So
what a nice example.
Yeah, so this, I mean, the thing is that this was a known example. It was a known example from the model theory of differential fields. And the question, it was just translate it into some common terminology like constraintness or isolation. If you translate that to constraint, then it's clear that this is really the counterexample. Now, of course,
it's clear once you see it.
It's clear once you see it. It's clear once you see it.
I certainly didn't see it.
And yes, clear once you see it.
You asked me the question.
And now one can build counterexamples in different ways, but the ones that we know are all related to this Manning kernel.
Wow. Oh, that we know. That's right.
I'm not sure. Yeah, I mean.
Oh, that's interesting too.
Okay. I had to think about Ronnie's comments.
Yeah.
Because I thought that A sharp was always strongly minimal. So in this case, in case you have a simple evident variety, is the Manning kernel always just torsion points? Maybe the L points. Yeah, I guess. Okay, I need to think about that.
It's interesting if you look at Colchin's proof that a differential algebraic group which is torsion must be finite.
Yes.
Another comment.
Then
would you read the comment?
Yeah. You can see where.
Could you just read it loud?
Yes. No, I do not think that A sharp L is equal to A Tor. Always. I guess I mean Tor A. Always. Let me give you an example. Take A K as in Omar's presentation. Let K prime be K, be the differential field generated by A generic point of A sharp. Then transcendence degree. And it not complete. I think there's something missing in that comment at the end.
The most important part.
Yeah, then transcendence degree.
Always not equal to 1.
Yeah.
How is it complex?
No, to the comment.
It doesn't end in anything.
Yeah, maybe it wasn't finished type.
It's not finished.
So maybe we can wait. We can wait maybe.
No, there's a limit of 140 characters
There's so many characters they can.
The point this comment is missing. Has too many characters.
So whoever wrote that comment, is it possible to write another comment?
So yeah. Hopefully he'll write
another comment.
Please write another comment.
Yeah.
Yes.
I was saying that if you look at Colchin's proof that every differential algebraic group that's torsion is finite, it uses the fact that you're working in a universal differential field, so that you have in the group a generic point.
Oh, okay.
So it's finite.
Could you read it loudly for everyone who's watching?
Yes. Okay. So again, I do not think that A sharp L is equal to a torsion of A always. Let me give you an example. Take A, K, as in Omar's presentation, let K prime be the differential field generated by the generic of the Manning kernel of A. Yeah. Then the transcendence degree of K prime is finite. Then if L prime is the differential closure of K prime, then the sharp points of L prime contains the non-torsion point A. Right. The differential closure will contain the generic point.
That's right. His proof uses that.
Okay.
Yeah.
Thank you.
Yeah. Thank you.
Whoever wrote that comment. Thank you. Okay, nice.
Yeah.
Okay, so there you go. It's not always the case that the Manning kernel, the L points of the Manning kernel is the torsion of A.
Yeah.
Okay. Can people see those comments in the, I guess?
They can see
if they go to the
interesting comments.
It might be the case if K is the field of definition of. It's equal to the field.
Oh my.
So the people can see.
You mean a minimal? Equal means equal to the minimal field definition, or A or A field?
No, I get. No, it must be equal because it is A. It is A.
I mean minimal.
So those
Canonical
speaking
base.
for the who is watching. So if you want to see the comments, you can remove in the web address in the URL the WEB,
Firefox won't
and then you will see
nice.
the comments.
What's this or field of module?
I guess instead of K being the field definition, K, if K is the field of model, I don't know exactly what that means.
No, I don't either. What if K is the field of definition?
Then you get that the L points of the money kernel is the
Yeah.
torsion of A. Okay, good, good. Thank you.
Or field of moduli.
Yes, well, thank you.
I wonder if that's on.
Something to think about.
Where in that?
Okay.
Okay.
Okay, so this gives us the counterexample.
That's very nice.
This gives the counterexample.
Yeah.
Okay. So let me. So now we have this counterexample. Now,
That's completely model theoretic. It's
They just
interesting.
need to remove.
yeah, it's very interesting. These model
Yeah.
constructions. I mean,
Yeah.
yield the counterexample to the question. Okay. Now, I want to move on. By the way, I do want to say something before moving on. What is the transcendence degree? What is the least value for the transcendence degree here?
You mean
Over C. Sorry.
Algebraic
Yeah, this is so take a money kernel.
2 is the least.
2 is the least. That's right. That's right. 2 is the least. So this is now if I think it over C, I assume that K had to have transcendence degree. Oh, sorry. At least 1.
Yeah.
So over C, my counterexamples will have transcendence degree at least 3 over the complex. So over K2, and then K over the complex
okay.
1.
Yeah.
Yes?
Yeah. Yeah.
Right? So
Yes.
over the K2, and then over the complex at least 1, so at least 3.
Yeah.
So the point is that I can build counterexamples
Yeah.
for every Courle dimension from 3, 4, and so on. That's the point. I can build counterexamples for every Courle dimension at least larger than or equal to 3.
Mm-hmm.
That is it. Now for the Passon algebra part, I'm just gonna give the statement. Maybe I'll sketch a couple of proofs. Only have us 4 minutes. We'll just spend time on this. Okay, shall we have? Okay, now I want to move on to the Passon algebra part. Just reminder, sorry, before. In this talk, by a Passon algebra, I mean, in this talk, maybe a complex Passon algebra. A complex, affine Passon algebra. A is a finitely generated integral C algebra with a bracket, with a B bracket,
Oh, yes.
with a B bracket. Such that for all little a and A, the map. So this gives me, if I fix A, this gives me a map. It's a derivation. This is a Passon algebra. So, I mean, if you have seen what a Passon manifold is, this is just a Passon algebra structure. A Passon manifold is just simply a manifold with a Passon algebra structure on the algebra of smooth functions. So this is it.
Yeah.
This is what a Passon algebra is. It's just basically a Lie algebra such that the Lie bracket behaves as a derivation for each fixed point here. Okay. Now, I want to talk about something called the Passon gives me a Morgan equivalence. Passon gives me Morgan equivalence. So the original or classical gives me a Morgan equivalence. It's something about 3 class of prime ideals. There are prime ideals which are called rational. I'm going to talk about that. There are prime ideals that are called primitive. And there are prime ideals that are called locally closed. And the Digny-Mori equivalence says that these 3 sets are the same in some cases. So that's the general framework. You have a setting, and you try to check maybe in these settings, these 3 classes of prime ideals are equivalent. That is the Digny-Mori equivalence, okay? So it says that primitive, locally closed, and rational. These are all classes of prime ideals. Now, in the Passon setting, you talk about Passon primitive, Passon locally closed, Passon rational. What do I mean by that? Now, it's very natural. What do I mean by an ideal to be a Passon ideal? It means that it's closed, it's stable under the application of the bracket. So this is a derivation, right? This is just a derivation. Yeah. So you're saying it is a differential ideal for all these derivations. That's a Passon ideal. Yeah. Passon ideal is just a differential ideal with respect to all of these derivations as you vary little a. So now here we can ask, okay, is Passon primitive equivalent to Passon locally closed to Passon rational? In this context, it is known in the Passon context. It is known that 2 implies 1 and 1 implies 3. That is known. Locally closed implies primitive, and primitive implies. Oh wait, yes. 2 implies 1. So locally closed implies primitive implies in the Passon setting, okay? But by the Passon setting, I mean this setting. So now there was a question. Does 3 implies 2? That was the Poisson-Dixmuir-Moulin conjecture. If these are all equivalent. Okay, so in the work.
So the equivalent, the original equivalent doesn't cover the Passon case.
No. The original equivalence is just in the algebraic setting. And in that case, under some mild assumptions, we also know that 2 implies 1 implies 3, but there are examples where they are not equivalent. Examples where they are in the algebraic setting. In the Poisson context, we again have these implications.
What about differential context?
That's a good question, which I'm pretty sure what we did, it also answers the question. So in the differential context, I'm pretty sure that these proofs for the Poisson context
should work.
They should work. I mean, I'm pretty sure this Poisson context is essentially having derivations, right? And now I think what I'm going to talk about right now will prove that these are not equivalent in the differential setting.
They're not equivalent.
They are not. So 3 does not imply 2. However, what the work that we have shows that 3 implies 1. So this is the work that we have. 3 implies 1. So I'm pretty sure in the differential setting, 3 implies 1. So 3 implies 1, but not 2. So in what we have is that in this setting, primitive is equivalent to rational, but there are ideals which are rational but not locally closed. So I want to finish by giving the counterexamples. And it's going to be very natural. Okay. But first I need to say what it means. First I need to say what it means. So what is a Passon rational? Passon rational. If so this is a Passon rational prime. So P is prime. And if I take this, take the quotient. This is a domain. Now take the fraction field. Now in the fraction field, I also have a Passon algebra structure. This is a Passon algebra. This is a Passon ideal. I have a this is like a differential setting. So this is very similar to the differential setting. And now what I ask is that all the constants, we have these derivations, right? So the field of constants, in the sense of the Passon algebra, so has no constants. I hope this is clear. So what I'm saying here,
Compared to A mod P?
yes. This is M with P to the fraction field. I.e. if f with a is equal to 0 for all a in the fraction field, in this fraction field, then a is
And this is the definition of rational.
This is the definition of rational.
Right.
Once you mod out, you get non-new constants in the fraction. So maybe now you're seeing kind of the analogy with rational with our assumption of non-new constants. Basically, very similar, right? Now, Passon, locally closed, right? It just means that if you can take the Passon spectrum and Passon locally closed means P is locally closed in the Passon spectrum. The Passon spectrum effect. Now, but remember, this has a very similar flavor as the constraint elements. I told you constraint elements, something is constrained if and only if it's locally closed in the differential spectrum. This is what they are similar in that sense. Okay.
What's P spec A?
Oh, the Passon.
Passon. Oh.
Sorry, yes. You take all the Passon prime ideas.
Nothing to do with this P.
Nothing to do with
Yeah.
it. This is P of Passon.
Right.
That's right. Okay. How am I going to build? So what I want to build, what I want to show is that
So it's constrained for every derivation.
for every derivation.
Well, this means it's constrained.
Yes. Yeah. Remember that in the differential setting,
Yeah.
this was equivalent to constraint. So
Yeah.
now it's for every derivation. So I want to build a Passon algebra where Passon algebra where 0 is rational.
You have a,
Yes.
you have a generic point P that works for all the derivations at once.
How is that? So I take, you mean
Yeah.
here?
Yeah. Do you have a generic point for your Torsion prime that is locally closed, that is generic for every derivation?
Derivation sub
Do
A.
you have,
Oh,
you have to choose different ones?
Do they vary with A?
Yeah. Because you have different derivations, right?
Yeah.
Yes, yes,
So now when you talk about generic points,
yes.
then you're talking about different,
It should be the same.
different differential prime ideals.
Yes.
Right.
Now these derivations are not commuting, right? So this is
Right.
No.
this is a bit
No.
different from the usual setting, right? So even talking about, I'm not sure how the behavior of generic points will be in this setting, But something I can say that might be related to that is that, you know how we have constraints, this G, the constraint. Again, here the point is that locally closed means finding a constraint.
Yeah.
Finding a single element in the algebra.
Well, is that what you locally mean? That's a single one for all the derivations?
Yes. It means that you can find a single element in the algebra such that if you, I don't want to say this, if you localize, so remember the constraint meant when I localize, I get differentially simple. That's another way to say constraint.
Yes.
Once you localize, you have no differential ideals.
Right.
That's equivalent.
So that is built into the definition of locally closed?
So locally closed here is, again, something is locally closed if you can find an element here such that when you localize, right, you have no Poisson ideas. You have no trivial.
So it is built in.
For all A.
So it is built in.
Yes.
Built in that there is a single G.
There's a single G for
G
all of
that
them.
constrains it.
Yes, it's a single G constraint.
Yeah.
Yes.
Okay.
Okay, so this is what I'm gonna do very fast. Just building a Poisson algebra where zero is rational but not locally closed. Okay, so how we're gonna do it? We'll let R be a differential ring given by our previous construction.
Yeah.
We have this construction from before. We have this was the function field of the Manin kernel.
Oh.
This is what I mean by the construction before.
Yeah.
Which satisfied what? It was a finitely generated different algebra with a derivation,
Wow,
no new
yes.
constants, and it was not constrained.
Right.
It was not constrained. Okay, what does it mean? So no new constants and not constrained means zero is not locally closed in the differential setting. So this R was non-new constants.
Yes.
And zero was so not constrained. It was not constrained. So that means that zero is not locally closed. It's not locally closed. Okay? In the differential setting. Now let's pass it to the Poisson setting. Let's pass this example to the Poisson setting. So consider the Poisson algebra. I'm going to consider the polynomial ring over R. But I need to tell you what the Poisson algebra is, right? I need to build a Poisson algebra.
Oh, what is it? Oh, R is that?
Yeah, R is the one given in the previous example, right? So I want to build a Poisson algebra in the polynomial ring over R. How am I going to do it? So P and Q. So P and Q are polynomials over R. How am I going to define this? Well, I can take delta applied to the coefficients of P times the derivative of Q with respect to T, the polynomials, minus the derivative of P with respect to T times.
Yes.
And that gives me a Poisson bracket.
The usual non-standard.
This is the standard. So you can do this whenever you have the derivations.
Yes.
You can define Poisson bracket this way, or Lie bracket.
It's Ritz G sub S.
Oh, really? Oh, I'm gonna look that up.
He proves there are two possible structures on the GA without
On the
a
algebra?
GA. One is this, and the other is the usual abelian one, where the bracket is zero.
Oh, okay.
So it's in two extremes.
Okay. I didn't know that. Okay, I'm gonna look it up.
Oh, look up his papers in 1950 on differential groups.
Differential groups. Okay, I'm gonna look that up. I didn't know.
Yeah.
Okay, so now he's gonna finish by saying, with this Poisson algebra structure, you can show that because this guy has R has no constants, then RT will satisfy that zero is rational, which just means no new constant, but now in the Poisson setting.
Right. Oh, this is very
So
nice.
R has no constant in the differential setting. Now RT has no new constant. Once you pass to the fraction field again,
Right.
no new constant in the Poisson sense. In the Poisson sense.
Oh.
The other condition that locally closed, again, this guy If you take all the prime differential ideals, the intersection will be 0. Right? When you pass this, and you take all of those and generate them above, you're gonna get a family of prime Passon whose intersection is again 0. So 0 will not be locally closed.
Yeah.
That's how you build contracts.
Very nice.
The P upper delta means differentiating coefficient.
The coefficients of P.
Yeah.
So I want to finish with this. I think we'll talk one more
Good
time.
timing there.
Yeah. I want to say a bit more, but
We'll say a
this
little bit
is-
more.
yeah. So this is it. This is the
you
contract
wanna say.
time. This is what I wanted to say. Okay. For classical examples in differentially closed fields, we built examples in Passon algebra that answer this question about the Dix-Mia-Moldy equivalence. This question posed by Gordon and Brown.
Say the names again with the equivalence.
So the equivalence is called Dix. Yeah, I think I erased it. This equivalence is called the Dix-Mia.
Oh, yes.
This is a famous Dix-Mia-Moldy equivalence. And this question about in the Passon setting was asked by Brown and Gordon. So Brown and Gordon, they proved that this Dix-Mia-Moldy equivalence is actually true if you only have finitely many prime Passon ideals. And under other, maybe more general conditions, has been proven as well. So, but they asked if this was true, and it's not because of this example. So it was nice that these examples came from the model theory of differentially closed fields.
Yeah. Do you have anything written up on this?
We're writing this up, and
you're just in the process.
I think that soon we'll be submitting and posting. I would say soon, yeah.
Soon.
Soon.
And it'll be on your website.
I'll post it on my website. Yes.
Very good.
So yes.
Yeah.
All right.
Very nice. Thank you very
Yeah.
much.
Good. So.
Yeah,
Okay.
so we should run and
No
eat
more
lunch before.
Yes.
Very, very nice.
Yes.
Another comment.
Oh, there we go.
No.
Omar should not think too hard about my comment. I was assuming that K was the field of definition. Okay. So which in that case, your comment.
Yeah, so was
seems
I
to be
actually,
true.
my comment about the question was whether you had it in this case as well as. Oh, no, mine didn't, no, I didn't assume that.
You didn't assume that the K was the
No.
field of definition. Okay.
No,
Okay.
Yeah,
Okay.
that's such
But
an
this
interesting example.
this is nice.
And what did Wyszowski prove? Ray, the equivalent, you had some other names about whether 3 implies 1. 3 implies 1.
You mean for this
Yeah.
for this equivalence?
Was there a model there?
So for the Dix-Mia-Moldy equivalence,
Yeah.
so we have that 2 implied 1 and 1 implied 3,
Right.
right? So
2 implied 1.
2 implied yeah, right. And then in the work we have, the one that we're doing right now, we
You have that 3 does not imply 2.
3 doesn't imply
imply 2, and that 3 implies 1. I didn't show it. I didn't give the argument.
You proved that too.
But it is in this work that we're doing. This is proven in the work that
3 implies 1.
3 implies 1. This work of Jason and Stefan and Ibrahim. 3 implies 1. That one, and it's very nice.
Omar et Alia proved 3 implies 1.
And it's nice because actually,
nice.
it's actually quite nice. That proof of 3 implies 1 is nice because
Yeah.
of the original question, the very first question I wrote down. It's true as long as you have that all the ideals intersect a finite dimensional vector space.
Okay.
Under that extra assumption,
Yeah.
then
Yeah.
it's true.
That's very nice. I like this
And
too
then
because
it goes.
A sharp is a differential algebraic group.
Yes, yes. It is. It's a very nice one. All right, good.
We like that.
Yes.
Oh, that's interesting. A counterexample that involves a differential algebraic group.
Yeah.
Usually it doesn't involve counterexamples.